Alrighty, so as promised, here are some examples regarding exponential growth and decay using calculus. So for these questions coming up, you wouldn't be able to solve these if you didn't have any knowledge of calculus. So kind of makes you feel good if you know how to deal with rates and you've seen the last video. It's kind of putting that derivation to use. Okay, so for this question here, the population of Mathtown is growing at a rate of 7% per year. Okay, so the rate is proportional to the population. Find a differential equation to express this. Okay, so that's our first thing we want to do. Okay, so the first thing I see is I see this word rate, and that's kind of what all calculus is about, is rates. So if we call P the population, dP by dt, right? The rate of the population growth is equal to 0.07, right? That's 7% times P. Okay, so this is our K, this is our rate constant. The percent growth every year is our constant there, so that's the differential equation that we can use. Okay, so write an equation to represent the population as a function of time if there are currently 5,000 people. Well, we saw in the last video that any population, I used A in the last video, but for this one, let's use P. P equals P naught times E to the power of KT, right? Well, all we need to do is put in the conditions that we know. So P, right, that's our independent, or that's our dependent variable, right? So we have to have this 5,000 here, right? This is our P naught times E to the power of KT. T is our independent variable. We know what K is, right, from the last, from part A, so to the power of 0.07 T. So this equation is going to let us figure out what the population or the time is, which is super helpful. And notice we got that just from knowing what the rate is. All that we knew was that it was increasing at 7% per year, and there are currently 5,000 people, right? That was our initial condition. So there are currently 5,000 people at t equals 0, right? But it's pretty cool that we can figure out this entire equation just from knowing the rate and how many people there are at this time at the initial condition. So for part C, the predicted population in 20 years. Well, we kind of did the hard part, right? Because 20 years, I think of that as a time. So, and we're trying to find a population, right? So P equals, we think of 5,000 to the power of, or times E to the power of 0.07, right? Times 20. Okay. And you have to make sure, like, if this was 20 months or 20 minutes, right? You have to do that unit conversion because the rate that we found was 7% per year. If this rate was 7% per month, we couldn't just put in 20 for t, right? They have to match. You have to make sure that your time units are all the same. But in this case, it's okay. So 0.07, right? 0.07 times 20. This is e to the power of 1.4 times 5,000. So you just multiply that. Okay, so this is going to give you 7,000. This is going to give you 7,000 people. So if the population rate constant stays consistent at 7%, over the next 20 years, it'll increase by 2,000. So it'll go from 5,000 to 7,000. Okay, so that's part C there. And how long will it take for the population to triple? Excuse me. So what we want to do is, our original equation said we could find the population P, right, by taking the initial value of the population, P naught, and multiplying it by e to the power of kt. So notice how if we divide both sides by P naught, the P naught will cancel, right? And we have this ratio here, P over P naught. So this is just the population that we have now divided by the population that we started with. So if the population triples, this fraction, this ratio is just going to be 3. Okay, so this is just going to be 3 on the left side. 3 equals e to the kt. What is k? Well, k is just 0.07. K is 0.07 for all these questions. For A, B, C, and D, it's all the same. And now we can kind of just use our knowledge of logarithms. We're going to need to use a natural log for this question. So if we take the natural log of both sides, right, we can bring this 0.07t out to the front. So 0.07t times the natural log of e, right? The natural log of e is just 1. So natural log of 3 equals 0.07t. We can just divide both sides by 0.07. Okay, and let me just put that in my calculator here. So the natural log of 3, 1.1 divided by 0.07. So that's going to give us about 15.7. So remember, t is in years, so t equals 15.7 years. So that is saying with a growth constant of 7% per year, it will take 15.7 years for the population to triple. So that means that for this fraction, this ratio of population divided by initial population, that will be 3 by the time in 15.7 years. So that's kind of how you can figure out this question here. Hopefully that makes some sense. Here's another question involving pressure in a tire. So this is completely different, right? But it's the same kind of idea because we're dealing with rates and growth. It's all the same idea. Even though we're going from population to pressure in a tire, it's virtually the exact same question. Okay, so it's saying air leaks out of a balloon at a rate of 0.3 psi per minute. Okay, so those are units when the pressure is 41 psi. Solve for the rate constant. Okay, so that's the first thing we're going to do. So what I see is the air leaks out of the balloon at a rate of 0.13 psi per minute. So I'm going to say I'm going to use p again in this example. So the change in pressure with respect to time, right? That equals if the rate is proportional to some constant k, it's going to equal to k times p. Okay, so what did it say the rate was? It said the rate was 0.13, so that's our dp by dt. Okay, if the pressure was 41 psi at the rate of 0.13 psi per minute, that means that our p is going to be 41. So 0.13 equals 41k. Now dividing both sides by 41, 0.13 divided by 41, that's 0.0032 about. 0032. I'm actually going to keep a couple decimals here. So 0.00317. Okay, so that's going to be our k for every part of this question. Now, what's the differential equation going to be subject to the initial condition in part A, right? So the differential equation is going to be P equals, so the pressure is going to be equal to the initial pressure times e to the power of kt. And also, I forgot to mention the k up here, it's not positive. I should have put that in. Maybe it makes some intuitive sense to you, but if the pressure is decreasing, right? The pressure is decreasing at a rate of 0.13 psi per minute. That means k is going to be negative. Anytime k is negative, that means that the population or the pressure or whatever you're dealing with, that's decreasing. So it's a negative proportionality. Okay, so P equals P naught times e to the kt. That means the pressure at any given time is going to be the initial pressure. So let's say the initial pressure was 41 times e to the negative 0.00317t. This is our function to represent the pressure. Okay, subject to the initial condition of 41 psi. So what's the pressure after 20 minutes? Well, that means we're solving for P, right? That means we're going to have to know our time, which we do. We know it's 20 minutes times e to the negative 0.00317 times 20. And again, I cannot emphasize this enough. If this was 20 hours, you could not put in 20 for T. And that's because the rate that they gave us was 0.13 psi per minute. It wasn't 0.13 psi per hour or per year, right? The units have to agree or else you're not going to get the right answer. All of this is useless if you don't use the right units. Okay, so that's super important. Now 41 times e to the power of our k times 20. So times 20, let's take e to the power of that times 41. Okay, so that gives us 38.48. And the units for this is PSI, right? That's the pressure. And this should make some intuitive sense because we started with 41 PSI. If we know the rate is decreasing after 20 minutes, this number should be less than 41, right? So for part D, it's asking us to sketch the graph of the situation. Well, we don't even need to, we can kind of look at this function and, because this is our function to represent the pressure, right? If the dependent axis is P and independent is T, this is kind of the function to represent that. But we don't even really need to look at that. All we need to know is the initial pressure, right? If this is P and this is T, we know the initial pressure is 41. It's going to slowly kind of decrease down. It's never going to quite hit zero. There's going to be a horizontal asymptote at zero, but as time increases, it's just going to flatten and get ever closer to zero. So remember in the last question, what was our time? Our time was 20 minutes. So at 20, right, if we went straight up from here, this pressure would be 38.48. So if you were to graph it, you could find it. If you graphed it on Desmos, you wouldn't even have to do these calculations, but it's good to know kind of where all these numbers come from. So there are two examples. They're very different, but quite similar in terms of how to solve it. So just remember, if a population is growing, right? For the question above, it was 7% per year. That means that our K, our rate constant, is positive if something's growing. It doesn't have to be greater than 1, right? It just has to be positive. And if the population or the pressure or the amount of money you have, whatever it is decreasing, that means our K is negative. And even I kind of forgot to tag that negative in there, but it's super important. So if your K value is negative, right, in your exponent, that means that your graph's going to look something like this. It's going to decrease over time, right? It's going to flatten out. So hopefully that makes some sense. And yeah, that's kind of the basics. I'm going to go over in my next video something called Newton's law of cooling. It's a similar idea, just a little different, but that's kind of the intuition behind the formulas you've seen before. Now there's just kind of a essence of calculus in there for you to work with and add to your toolbox. So yeah, I'll see you in my next video.